How do physical qubits achieve fault-tolerant quantum computing? Imagine trying to keep a delicate soap bubble intact while walking through a busy street. That's similar to how physical qubits stay stable in a noisy environment. Quantum computers use tiny particles called qubits to perform calculations, but these qubits are very fragile. They can easily lose their quantum state because of environmental noise, interference, or mistakes in operations. To make quantum computers reliable, scientists have developed methods to protect these qubits from errors. The key idea is to use many physical qubits together to create a single logical qubit. Think of it like building a strong wall from many small bricks. If one brick gets damaged, the wall still holds. In quantum terms, this is done through quantum error correction. These methods spread the information across multiple physical qubits using special codes, like surface codes or quantum low-density parity check codes. These codes allow the system to detect errors by measuring extra qubits, called ancillary qubits. These ancillary qubits do not hold the main information but help identify where errors happen without disturbing the logical qubit itself. The process begins with encoding. Multiple physical qubits are entangled from a logical qubit that can survive errors on individual physical qubits. Next, the system measures the ancillary qubits to find error patterns, called error syndromes. Classical algorithms then interpret these syndromes in real time and tell the system what corrections are needed. This way, errors are caught early and fixed before they cause bigger problems. Fault-tolerant quantum gates are also crucial. These are special ways of performing operations that prevent errors from spreading uncontrollably. Techniques like transversal gates and lattice surgery allow logical operations to happen while keeping error correction intact. For quantum computers to be truly fault-tolerant, the error rates of physical qubits and gates must stay below a certain level, often above 99% fidelity for 2-qubit gates. When error rates are low enough, increasing the number of physical qubits can make logical errors arbitrarily small. Building large-scale quantum computers involves making these systems modular. This means combining many small, reliable units of quantum memory with processing units. This modular approach helps scale up to thousands or even millions of physical qubits needed for complex tasks. Without fault tolerance, errors would pile up quickly, making results unreliable. That's why fault-tolerant quantum computing is so important. It allows quantum computers to run long and complicated algorithms, like factoring large numbers or simulating new materials, with high accuracy. In simple terms, physical qubits achieve fault tolerance by being part of a carefully designed system that detects, corrects, and contains errors in real time. This makes large, reliable quantum computers possible and opens the door to solving problems that are impossible for classical computers.